Yeah, so I want to talk about disk formation. This follows up a little bit. We've heard related talks from Claude André. Vadim talked about this, I think, kind of interesting question we're sort of trying to grapple with. So, for the last decade or so, or a little longer, we've been able to make kind of realistic-looking disk galaxies like these in Zoom cosmological simulation. But I think what's interesting is we still don't know kind of the complete story on why, like what's actually going on to allow these things to form. And then obviously we're also learning a lot from the real universe about what disks look like, or they don't exist at high redshift, they emerge over time. And also the Milky Way is particularly interesting. We're going to sort of put all that stuff together. Work I'm going to talk about, you will hear later from Olti Mirtai, talking about related work. But I'm also going to talk about work that was led by Luke Shah, who's actually an undergrad at UCI doing stuff on galaxy shapes. I'm going to tie galaxy shapes to sort of the formation of disks. He's been more or less advised by Courtney Klein, who's doing a lot of stuff with making mock images of our galaxies. I'm not going to talk about that today, but she's played an important role in sort of enabling all the stuff I'm going to talk about today. Fiona's going to talk next, and I mentioned that Vadim is doing work on trying to get a handle on what's going on with these galaxies forming them early and how they spin up at all. So I want to just sort of show some stuff that you've probably seen before, but the Milky Way is revealing kind of some interesting things thanks to Gaia on its formation history. A paper that I thought was particularly interesting was this nice work by Vasily and Andre in 2022, where they were looking at in situ stars in the Milky Way. So this is not stars that were accreted, but they've made cuts to look at Milky Way stars and track. Basically, it looks like there's a characteristic metallicity where the Milky Way kind of spun up. So in low metallicity stars locally that are in situ, the galaxy really is not spinning. But somewhere around a metallicity of -1, you start to see this kind of thin, thick disk spinning stars in the galaxy are sort of emerging. And then at late times, you eventually get to 200 kilometers per second. So this idea of how you go from this kind of turbulent, chaotic, early Milky Way, where there really was no disk, to this disk that spins up with time, there's something there, and it's interesting. It looks like the Milky Way spun up. It wasn't discussed too much in this paper, but it's there, that the other thing is the velocity dispersion of stars that are rotating, the sort of spread in those tangential velocities goes way down at late times, and that's a period of time I'm going to call cool down. So there's sort of this spin-up phase and then this cool-down phase that corresponds to the thin disk formation of the Milky Way. This was done really nicely by Vedant in a nice paper that I think is about to be published, again using Gaia data. And now they're characterizing the orbits of stars in a way that we've been doing for the last couple of years with some of the fire simulations, where and that it's a popular way of doing it. You measure the specific angular momentum of the particle compared to the specific angular momentum it would have on a circular orbit with the same energy. And this creates a nice dimensionless quantity such that at 0, it's kind of sort of random. But then at 1, it's like a super edge-on thin disk where all the orbits are circular. And what you see is there are these 3 distinct phases here that's drawn out clearly. At low metallicities, below -1, it's kind of this sort of random thing, this chaotic random thing, this spheroid. And then there's this period of time where you have the thick disk. So it's not perfectly circular orbits, but it's clearly co-rotating. And then there's this period where it just thing snaps to 1, where it's this thin disk phase, right? So you have this kind of early chaotic phase, you have a spin-up time, and then at some point you have this thin disk phase snaps into being. Really, it's distinct phases and not kind of gradual, which is interesting. This was particularly interesting to us because over the last few years we've been studying some of the disks that I was showing pictures of before, and it looks like there are these phases in a lot of the simulations, and a lot of the fire simulations. In particular, this is a figure that Anna Yu made, and what's plotted here in red is the circularities of stars at birth as a function of look-back time. So early on, the circularities are pretty chaotic. It's jiggling up and down. This is sort of bursty, chaotic phase. And then at some point, they start to align, they spin up, and then there's another point where they snap to 1, and that's the thin disk. If you look at where those stars are now, The features are actually very similar. It just becomes more regular and smeared out. You track it even archaeologically, as we're doing in the Milky Way. If you track it archaeologically, you see it there too. Olti will show this later, but you can make the same plot that Chandra et al. Made. If you use the same color scheme, etc., you can plot them all. And it's remarkable how similar these two things look. This is this galaxy, Romeo, on the left, and on the right, ChatGPT tells me this is a picture of the Milky Way. Amazing, we can take pictures like that today on the right. It's pretty cool, right? I mean, qualitatively, there's very similar features here where you have this proto-galaxy, you have the hot, thick disk, and then you have the cold, thin disk, kind of like you see in the Milky Way. And the question is, what the heck's going on here? Let me just sort of show you pictures because it's very nice. I think this is useful. Here's a snapshot in phase 1 where things are chaotic. This is what they look like when the stars look like when they were forming. This is where those stars are at z of 0. So chaotic, crazy thing, turns into a spheroid today. During phase 2, you have this clumpy, chaotic disk. It's spinning. This is after spin-up. You look where those stars are today, it's a thick disk. And then in phase 3, forming in a thin disk stays in a thin disk. So spin up, cool down, and what's the reason for these two features? I want to talk about cool down. Olti's going to talk about spin up. Because I made Olti do the hard part. Because I think we understand cool down, and I made Olti talk about the hard part. He's doing the hard part. Okay, so Claude Andre talked about this, but I think it's useful to show these pictures again because these are, I think, very useful. At early times, we have this cool dynamic inner CGM. The inner CGM virializes, and only after the inner CGM virializes do we start to see the emergence of this kind of disk phase. Early on, it's supersonic flows that are crashing in like crazy. At late times, it's gentle accretion, so that's important. Particularly, just to hit it over the head, if you look at the circularities of stars as a function of time in Romeo and Juliet, it's a pair of Elvis pairs. Elliptical at early times snaps to 1 at late times. That snapping to 1 corresponds to the point when the inner CGM virializes. You see this for all 12 of the systems we've looked at. Very tight. And it's really quite remarkable that this is what you see. Just to remind you what Claude Andre already discussed, this is also the time when things go from bursty star formation to steady star formation. So a lot of interesting things are happening. Thin disk, steady, prior to thin disk, bursty. Bursty, chaotic, whether it's a disk or not, bursty prior to this phase. We think what's going on here is that once you're in the hot phase, the gas is getting into the galaxy in sort of a rotating cooling flow in its subsonic accretion. What's happening here is there's enough time for the angular momentum to align and mix prior to joining the disk. The angular momentum distribution, certainly of dark matter halos, but also of gas in the halo, it's not like it's spinning like a ball. There's a tremendous range of directions that the gas is spinning, and only when you add them together vectorially do you get the spin parameter that we're used to thinking about. So here you can see that what the gray band is the width of sort of spins, Jz over total J, of the gas as it falls into the galaxy in this particular case. And it starts out wide, and it gets narrow and narrow and narrow, everything spinning in the same direction right before it enters the disk. This is the temperature as a function of time as the gas is getting into the disk. It's hot. When it hits the edge of the disk, it cools out. The reason why it cools out is because it's falling in. It's a cooling flow, so it cools. It shrinks a little bit, but when it shrinks a little bit, it compresses, it heats up again, so it stays hot all the way in. It does that until it can't compress anymore. The reason why it stops being compressed is it's angular momentum supported. When it becomes angular momentum supported, it can't compress anymore. It can't heat back up, so it cools right out. And it's angular momentum supported, so it just joins the disk right when it's angular momentum supported and cold. And it sort of lays the gas, it just lands into the thin disk in this very thin way to keep it thin. It's really pretty, and if you do this in a galaxy that's in the cold mode, that does not happen. The gas comes in cold, the angular momentum does not align. It does not align even once it gets in the disk for a while. It takes it a while even to align in the disk. By that time, it's formed a bunch of stars, and it's sort of nets. So this picture is that in the cold mode, accretion mode, you can form things that spin, but they're not very thin. They're clumpy and that stuff. You only form these thin, razor-thin disks if the gas is accreted subsonically. So just to hit this really hard, both of these halos have the same spin parameter. Both have spin parameters of 0.03. This one was fed by cold mode accretion. It's a mess. This one's fed by hot mode accretion. It was not the story that Joel told me when I was in kindergarten. But I'll forgive you, Joel, for that. That was... anyway, so to put this back up, we think that it's the hot mode that drives the cool down, right? So when you go into the hot mode, this is what's driving. And by the way, in the Milky Way, this is what's going on. That happened about 10 billion years ago. The Milky Way virialized about 10 million years ago, if you believe this story. The hot halo of the Milky Way. Pretty early. And ultimately, we'll talk about spin up. In the time that I have left, I want to now switch to talking about shapes. And because shapes are, of course, related to this morphology question, it's just sort of a different way of looking at it. This is this work done by Luke. And just what I'm going to do is characterize things by this typical way of a triaxial ellipsoid, a short to long axis ratio compared to intermediate to long axis ratio. If you live in this bottom right corner, you're a thin disk. If you live to the far right upper corner, that's just a ball. And if you live in here, you're a pickle. You're an elongated pickle. So what we're going to do first is just going to take all the stars in Romeo, sort them by age, and measure the shapes of those ages of stellar populations. This is what you get. The oldest stars are yellow. The youngest stars are sort of pink or purple. And two things you notice. Young stars live in a very thin disk, kind of what you would think. The old stars live in a spheroid that's very round. Everything's just crammed to the right. And, just to show you what the pictures are like, the bits seem to make sense. This is the young stars. They live in a thin disk. It's very round. There's a very small axis ratio. And these are the old stars. They live in a spheroid, round, too. A little bit flattened, but... And then, just to sort of make it clear, there's no pickle population here. It would be sort of weird, but it's still kind of interesting that we don't. Today, this is archaeological. Not much of a bar there. I mean, there's, maybe if you, we have some runs that have things that sort of look like bars, but not this guy. On the right is if you go back in time. So now, what were these stars doing when they were forming back in time? And you see, you don't have to go back very far, 4 billion years, and then you start getting things that are sort of moving around. They're not as round, and then things go crazy. Back here, you're actually having spheroids. And then you even have this very short-lived little, short-lived pickle phase down here where you get this kind of elongated structure. If we're interested in bananas, I'll just sort of show you one of these snapshots. It sort of looks like what, we've heard about. Folks have studied this. There is a little bit of a period of time where this thing really does look like a pickle. It seems to be tracing what's going on, I think, with the dark matter halo. The important thing is this is not super long-lived. You have phases that look like that, and then it will go back to looking like a spheroid over time. And, we have lots of pictures to look at. So, but I guess an upshot of this is, and maybe it's obvious, but it's still kind of fun to see, is that the stars that are in these phases, this is not like an equilibrium phase. Those stars don't stay looking like a pickle. That does not last that long. And even over the course of, half a billion years, the young stars are changing shape in what they look like. And they got round, right? So they were not so round when they formed, but then over time they relax. Getting relaxed, and they stack up to the right and they get round. Yeah. Yeah. It's not exactly the same stars, but it's very close to the same stars, and we're going to do that right in the final version. There's a little bit of accreted material living here, but not much. There's some accreted material here. And that's mostly populating at large radius. But yeah, they are like 90% the same stars, and we need to cull out the accreted ones. Yeah. So I'm going to conclude. So it certainly looks like the Milky Way has undergone these three distinct stages of formation. There's this kind of chaotic random phase, there's this thick disk phase and the thin disk phase, and what I've called the spin up, the transition from 1 to 2 is called spin up, and the transition from 2 to 3, this cool down. It's during this chaotic random phase, at least in these particular trajectories, that you see these funny shapes, right? You see the pickle phase, you see some of these other phases. Those are not, at least in these simulations, like permanent phases. The things are not even in quasi-equilibrium. The shapes are changing very rapidly during this chaotic random phase. At some point, things start spinning up, and then at this late time, you get this cool down. It really does look like this transition to cool down really has to do with the gas getting in the subsonic accretion mode. And it's this subsonic mode that allows the angular momentum to align prior to joining the disk. That does not happen in the cold mode. The stuff, even if it's got angular momentum, it's not super aligned when it comes in, and so the disk is kind of turbulent and messed up. And so you're tracking these over time. I will mention very quickly, since Joel asked about it earlier, there's a student who I hope will be here next summer, Fofi, she goes to Fofi, who's going to be looking at these effects when we have black hole feedback. Because we obviously know that if you have a quenched galaxy, it's not a disk anymore. But we want to understand this sort of dynamical evolution in systems when they're quenched and when they're not quenched, sort of track these features. So we're well aware of the fact there's no black holes. What we'd like to do is look in models that have this black hole feedback and see how this affects things at the other end once they're not disks anymore. Okay, I'll leave it. Thank you.
Yeah, just a quick question. So when you were showing the morphologies of the young stars and their evolutions with time, were any of those phases, whether prolate, spheroid, or disky, affected by merger histories?
They can be. So were these phases affected by merger histories? I mean, we haven't done like a detailed study object by object, but generally speaking, during this chaotic phase, there's all kinds of stuff going on, and sometimes there's mergers and sometimes they're not. The feedback is so strong that these things are kind of so turbulent that mergers don't really add that much energy to the system. The other thing we've noticed, I mean, obviously one-to-one mergers destroy disks, but even once the things are in these thin disk phases, they're pretty robust to sort of 1 to 10 mergers, and they might create a little starburst, but they don't scramble the orbits that much. But you will notice that the disks in young stars kind of slosh around a little, and sometimes that is a merger, so that it can change things a little bit.
Very interesting talk. I'm really curious whether this agrees with some of the data on like the spin of the CGM. There's been studies using quasars to probe, galaxy halos to measure the magnesium-2, and a little bit the O6.
Yeah.
And the magnesium-2, low ionization gas, right? It seems to all be co-rotating with the disk.
Yeah.
But you're telling me it's the hot gas that should be co-rotating. So the magnesium-2 is then what's cooled down?
The cold gas is also co-rotating. We worked on that too. It's just not as well aligned. It has angular momentum. It definitely has angular momentum. The problem is it's just a little bit misaligned. So it has the spin. In fact, that it has even a little bit more total vector summed angular momentum than the hot gas. The problem is just a little bit misaligned. So that's why it has this at all. But it's a little bit clumpy and disordered because it's not so well aligned when it lands. Now the hot gas, there's definitely a predicted signal as well. Jonathan Stern wrote a really nice paper on that earlier. I think it's out now. It's already, I think it was just published, making predictions for sort of looking at this hot gas signal as well, which I think should also be robust. So that is, the magnesium-2 I think should be spinning. It's just not super duper aligned, but it should co-rotate.
And do you have a prediction for the O6 at the intermediate temperatures?
I don't remember if done. I don't think we've done that. Yeah, it should co-rotate, but I don't know if we've done it. Yeah, it wasn't in the paper, but maybe we should do something specific for that.
Beautiful talk, beautiful work. When we studied the formation of these pickle galaxies a decade ago, the thing that we emphasized was that the pickle phase lasts only until the dark matter is no longer dominant in the center. So I was wondering if you checked that, and what typically happens in at least the Vela simulations is that there's a compaction event that produces a central spheroid, and that no longer, then those galaxies are no longer dark matter dominated in the center, and they quickly become rounder. So is that the pattern that you're seeing?
It's not quite as clean as that. I mean, we should chat with Olti later because he's tracked some of the dark matter fractions. I wouldn't be surprised. I mean, what you guys did, I think, is very, very similar to what we're finding. The compactification isn't quite as compactified in the fire simulations, and so I don't think we're quite seeing that as the origin of the transition. But it would only make sense to me that the things are dark matter dominated during this time. I mean, in this particular run, these things are like 10 to the 8, 10 to the 9 solar masses at most in the pickle phase. We know it's a dark matter dominated.
So Mark Huerta's company led a paper, I think it's 2018, where we compared with the candles HST data and found that in fact there is typically this compaction event that terminates the pickle phase and then is followed by a disky phase.
Okay.
So, and that turns out to be,
I mean, that hangs together. I mean, it makes intuitive sense.
Is Fiona here? No? Okay. Maybe one more question while Olti comes and sets up.
Hey.
Oh,
that's
hey.
awesome.
Thank you. Yeah.
I'm wondering if so do you understand what sets the time scale for this transition for the cooldown? Because in the plots they show that it's almost like an instantaneous switch, right? And so what happens with the intermediate regimes where you have part of the inflow in a cold mode, part in a hot, or if there's a transonic inflow and all that?
I mean, I wouldn't be surprised if that's also related to the spin-up phase when it's still half and half. And you know, the fact that it is so sharp is a little bit. I mean, you point that out. It's weird how sharp. And I don't know. I mean, maybe it is. There's some. You know, there really is a point where there's just a fraction of cold mode accretion just falls below some level, and you just don't see it. That's a great question. I don't know the answer.
All right, let's thank James one more time.